Hello and welcome everybody. Today's speaker is Gursharn Kaur, and she's currently a postdoc at the Biocomplexity Institute. She completed her PhD in statistics from the Indian Statistical Institute and worked as a postdoctoral fellow at the National University of Singapore. She holds a bachelor's degree in mathematics and statistics from the Bastinali University and a master's degree in statistics from the Indian Statistical Institute. Her PhD thesis work is focused on the reinforcement models with applications in load balancing problems and modeling opinion dynamics. And her work at the National University of Singapore has been focused on developing fluctuation results for the subgraph counts in large random networks. She is also interested in studying different shapes for random phylogenetic trees. And at the Biocomplexity Institute now, she is working on epidemiological modeling and analyzing missing infections. So a lot of things here. I am very excited to learn about some of her work today. So Gursharn, the stage is yours.
Thank you, Alice. And thank you for organizing this wonderful seminar series. And I'd also like to thank my friend Wasiur Rahman, who nominated me for this seminar series to the organizers. All right, so this talk is about interacting urns on a finite directed graph. I will try not to make it too technical so that it's accessible, at least some message can be taken by everyone. So, all right. So a little bit about myself. Although Alice already said things about me, so I did my PhD and master's in statistics from Indian Statistical Institute. And my thesis was mainly around urn models, where we looked at a class of urn models where the reinforcement is negative, or you could say not proportional to what you already see, not like what you see. So it's an opposite reinforcement, which is also important in the problems related to load balancing. And my postdoc, I will not go in too many details of these topics. So the postdoc at National University of Singapore, there I was working on a different problem. So that was related to subgraph limits for dense random graphs. And here at Biocomplexity, I'm working on completely applied stuff, which includes epidemiological modeling, code forecasting. We provide weekly forecasts through CDC. And also I'm now involved in some of the project that involves model calibration. So for today's work, my collaborator is Dr. Neeraja Sahasrabudhe. She's an assistant professor at Department of Mathematical Sciences at ISER, Indian Institute of Science, Education and Research, Mohali, which is in India. And the paper that I'm going to talk about today has been accepted for publication in Advanced and Applied Probability. So we are looking at the opinions of individuals on a network. By opinions, I'll come to what I mean by opinion. So network could be, you could look at two types of networks. One is the directed network, and you could also look at an undirected network. So by directed network, will mean that if there is an edge from one individual to the other, then one individual can influence the other individual. So the direction of the edge indicates the direction of influence here in this case. Now, I'll start this opinion dynamics, how this can be studied by introducing some basic urn model. So consider an urn which contains balls of two colors. By the way, I should mention that please feel free to stop me or ping me in the chat if there is any question, or if something is too technical, I'll try to avoid that. Or if you need more details, I can talk about that too. So starting with a very basic Polya model, suppose there is an urn that contains balls of two different colors, red and green. And let's say there are Rn and Gn be the number of red balls and green balls in the urn at any given time n. Then the dynamic is as follows. You select one ball uniformly at random from the urn. And if you see a red color, then you add a many balls to the existing red balls, and k minus a many green balls to the existing green balls. And then that's what your updated configuration at time n+1. So you can think of this timestamp as a day. So tomorrow, what you're going to see in the urn is whatever you have today plus a number of red balls and k minus a many balls of green color. And if in the uniform selection, so when we're selecting a ball uniformly at random, if the selection is a green, then we add the opposite. We are adding something else, k minus b red balls and b many green balls. So if I write that in a matrix formulation, this is my replacement scheme. So whenever I select a ball from the urn, if I see a red ball, I would add a many red balls and k minus a many green balls. And if I see a green ball, then I add k minus b many red balls and b many green balls. So what I'm doing here basically is I'm selecting one ball uniformly at random and adding a total of k balls. So if you see, the row total here is always k. I'm always adding a total of k balls. Now how many I add of red and how many I add of green, that depends. That is in my hand. These are the model parameters which is in my hand, and also the initial configuration or the initial urn that we began with. Now, so our goal here is to understand what happens in the limit. Now, in the limit, what we want to know that if I continue this process for a very, very long time, then where does the proportion of red balls converge? Now, let's say if I only add a many red balls and no green balls, whenever I see a red ball. So I only add a many balls of the same color that I see. In that case, this is called a Polya. So by Polya, whenever I'll say Polya, it only means that whatever opinion or the color that I have seen, I'm going to replicate that with additional balls. And the opposite color or the opinion is not involved in that reinforcement. So in the Polya case, the proportion of red balls in the urn at time n converges almost surely to a random number. A random number has a distribution, this Z has a distribution which is according to beta. And that parameter of that beta distribution are coming from the initial number that you started with and this the number of balls that we are reinforcing at any given time. Now, the very different urn scheme is when you add, let's say, instead of adding no balls of the other color, if I add even a small number of green balls at any given time, opposite color, let's say B, this is positive, then this proportion of red balls as n goes to infinity, this converges to a constant instead of this random quantity. Now, this change here is very interesting, that if you only have this replacement scheme as a diagonal scheme that you reinforce only what you observe, then the limit is a random number, has a distribution which is known. And if you add something, even however small it can be, then the proportion of red and greens in the urn eventually are same. So they are both half and half. We'll see almost equal number of red and green balls in the urn. Now this has a generalization, the Friedman urn, that if your replacement matrix R is such that it is irreducible and non-negative, it can be, this can also be generalized to more than 2 colors, but for now I'm only talking about 2 colors. Then the proportion converges to a vector or a number V, where V satisfies this, V is a left eigenvector of the replacement matrix. So in this case, half comma half is a eigenvector, left eigenvector of this matrix, and A plus B is an eigenvalue. So you know that now in these 3 special cases, what is the limit? So in this case, this is 2 is a generalized, a special case of 3 in this here. All right, so this is a simple introduction for a single urn. Now, what happens when you have more than one urn and you want to, so you can think of this one urn as one individual and the proportion of red balls or the green balls as an opinion of an individual. So if you have two colors in an urn, you can think of that as a individual having opinion between 0 and 1 for about some subject, and 1 minus that of the opposite of that subject. Now consider n urns, u1 up to un. You have this, and there are some white and black balls in those n urns. And we start with all these urns at time 0. We start with w01, b01, many balls in the first urn, these many balls in the second, and so on. Then what we want to do, that we want to update each of these urn. You can think of this urn as individuals. So you want to update the opinion of each individual or the number of white balls in each urn by adding a random quantity. Now that random quantity is a reinforcement that we are doing in the urn I at time t plus 1. Now the way we want to make it interacting is that the number that we add to the ith urn depends not only just on the ith urn, but it also depends on the other urns. I'll come to the network part also, which will be interesting. Now let's say ZTI is a proportion of white balls in the ith urn at time t. Then you can also define this overall average. So this is a bigger urn where you collect all the balls from these urns. And it's called this as a bigger urn. And the ZT is a proportion of white balls in this bigger urn. Then there's something called mean field interaction you can define, such that each individual, let's say you have this many white balls and black balls, then each individual looks at the bigger urn or the global opinion with probability P and its own opinion with probability 1 minus P. And then the reinforcement that you do in the urn I at time t plus 1 depends on the global opinion or the global proportion of white balls with probability P, with a weight P, and with weight 1 minus P, you look at your own opinion. So every time you select a ball uniformly at random, you first toss a coin, and if it is a head, toss a coin with probability P. If it's a head, you draw a ball from the bigger urn. If it's a tail, you draw a ball from your own urn. And then look at the proportion of this bigger urn or your own urn, which is defined in Z terms. Now, what is observed in this case is that this individual urn proportion is very close to the overall proportion of white balls. So ZT, remember that this is the overall opinion or overall proportion of white balls. So in this case, this ZT becomes a martingale. I'll not talk more about that martingale part. But the difference between ZTI and ZT, so if I go back, this is the ZTI, proportion of white balls in each of these urns, and this ZT is the overall proportion. The difference between this square difference, its expectation, this has this order, which depends on P. So P plays here like, there's a threshold at around half. So if P is bigger than half, then this difference is of order T to the minus 2P. If it is equal to half, then this is T1 by T log T by T, sorry. P more than half, this is around 1 by T. Now, what do we conclude from here? Let's not go into this very much about this. The important message here is this, that for any P, as long as your P is positive, it's not 0, the proportion of white balls or your proportion of the opinion of the ith individual has the same limit as the proportion of white balls in the bigger urn, in the global opinion. So for every individual, for every I, the proportion converges to the same limit. In this case, if we keep doing this process for a very, very long time, then the proportion in each urn of white balls will converge to the same number. Or in the opinion dynamic sense, if I say that each of these individuals, if they look at the bigger urn and update their own opinion based on bigger urn with probability P and their own urn with probability 1 minus P, then eventually they will synchronize because the proportion is converging to a constant number. So here there is no network structure yet. Now my collaborator Neeraja, she started this work with she looked at the interacting two color urns. So you have a Friedman urn. Let me go back here. Let's say you have these urns, but instead of this direction, you can also allow agents or individuals to interact among themselves. So if I first put this in a network form, so for the Friedman urn, what you are doing is that you are reinforcing same number of balls of the color that we observe. So in the diagonal, you will have the same constant number, and you also add opposite balls of the same color. Sorry, you add the opposite color of the same number. Then this interaction parameter P for this between 0 and 1, again, you reinforce according to this. Now you don't just have 1 and 0. This is not just a Polya scheme that you have just 1 or 0 here. You have alpha and beta. Then in this case, the synchronization depends on this eigenvalue, which is alpha minus beta by alpha plus beta, depends on the reinforcement scheme. This is similar to what we saw in the Polya scheme before, that if you have a Polya scheme, which is of diagonal form with 0 off diagonal entries, then the limit is a random number, but as soon as you make the off diagonal entries non-zero, the limit becomes deterministic. So she also observed the same, that if your beta is positive, if rho is such that this is positive, then the overall proportion converges to half, which is similar to the single Friedman urn we saw, and also the individual urn proportion converges to half. So eventually your opinion about ith individual's opinion about something remains half for a subject and half for the opposite of that subject as well. Now, she also worked for this class of interacting urn models. She also looked at the CLT, which is center limit theorem. Now, the center limit theorems are important for several reasons. You can do hypothesis testing with using the center limit theorem. You have this distributional convergence that ZT is converging to half, but how far ZT converges to half, and what is the limiting distribution. So ZT, if you subtract its mean, which is half, limiting mean, and take the square root T when rho is less than half, then the rate of convergence is is square root T. And for rho equal to half, this is like T by log T. And you also know the limiting variance here. That depends on the rho, which is the eigenvalue of your matrix. And also the number of urns. So larger the number of urns, the variance will be smaller here. Now we are making it now graph-based interaction. So graph-based interaction will first translate our previous problem to a network, putting urns on a network. So let's say you have these nodes where you put one urn at each node. Now, based on the previous problem where we had this proportion of individuals, and we were updating based on a function which depends on the interaction parameter P, and 1 minus P is a weight given to your own, this is 1 minus P for the overall and P for your own. Then this is looking at the average number in the overall bigger urn. Now, instead of that, what one can do is just look at a given. So this is when you are looking at the complete graph. So each node I is connected to all the remaining nodes. So this is a complete graph with all the self loop as well. So you can influence yourself and every other urn. Now, we want to not just look at the complete graph, but want to take a subset of this. So let's say you have a graph with maybe possibly smaller number of edges than a complete graph. Then we say that agent J or individual J can influence individual K if there is a directed edge from J to K. Now, again, as we did previously, that we'll place one urn at every vertex with balls of two colors. Then if there is a edge from one node to the other, then one individual can influence the other one. And again, here you can think of each individual's opinion as a proportion of any of the color in the urn which is placed at that node. Let's say for this example, take this example where we have this 4 individuals, but this is not a complete graph now. We have very few edges. This is a directed graph also. Then what we are doing, we are also looking at a generalized reinforcement scheme. So what we'll do now is we'll select one ball uniformly at random from each urn. And if the ball selected is white, then we give alpha white balls to all the neighbors. So let's say this node, if you draw a white ball from this urn, then it gives alpha balls to its neighbor, which is this one. And if there is a black ball, then we add m minus beta many white balls. So if there is a white ball drawn from this urn, then it gives alpha balls of white color to this urn and m minus alpha balls of black color to this urn. So this is a way how this individual can influence its neighboring neighbors. So this is one way that we have modeled the opinion dynamics on a given network. And you can so at any given time t plus 1, you can update the number of balls based on the previous number of white balls. And this alpha and beta parameter is coming from the replacement scheme. This is just an indicator whether a white ball was drawn from the urns. You can write that in the matrix form as well. So I'll go to the notation. Is there any question till this point? And or if there's anything I should talk more about this?
I would have a question about how the urns get updated. So these are all updated at the same time, right?
Yes. So these are all simultaneously. You draw one ball simultaneously from each urn, and then they're updated simultaneously.
I see. Okay. Thanks.
All right. Now, before coming to the main results, so we've assumed that there is no isolated node in the network. By assuming that there is no isolated node, it doesn't take anything away from us, because if there is an isolated node, that node is neither influencing any other node, nor it is getting influenced by any other node. So you can ignore that node. We are not losing anything by this assumption. And further, we classify our nodes in two classes. So we call a node J flexible if the in degree is positive, and it's called stubborn if the in degree is 0. And this is also very intuitive that if there is a positive in degree, then an individual is allowing its neighbors to influence itself. If the in degree 0, the individual is stubborn that he or she has its own opinion and does not get influenced by any of its neighbors. Now, the way that you are doing the reinforcement, so I take out the m. So if I go back and say that here also we were doing a constant row sum, that at any given time, whatever ball you draw, we add a total ball of m. Total number of balls that we are adding is m, whether you draw a white ball or a black ball. The total number reinforced is always m. It is always m is just a constant. So we are adding, it's not that we are adding something when we observe a white ball and we are adding something else when we see a black ball. The total is always same. The total always same also helps us, the total always same says that your total number of balls in each urn, which is Rn plus Gn, that increases linearly, and that increases linearly in M. Now this reinforcement scheme, I take out M because this M is not really important. What's important is this proportion A and 1 minus A, and I can write this as 1 minus B and B. And then this is called Polya type. This can also be classified as Polya and non-Polya. Polya if A plus B is equal to 2. So A plus B equal to 2, in that case, this 1 minus A will become 0 and 1 minus B is also 0. So this is Polya type if it's a diagonal matrix. And if it's a non-Polya type, if it's an off-diagonal matrix, but we still want A plus B to be still greater than 0. We don't want both this diagonal entries to be 0, that you're not reinforcing anything of the same color. And one more notation. So if you have adjacency matrix A of the graph, then A tilde by A tilde, we just denote scaled adjacency so that the column sums become 1. That's a weight that you're giving. By giving this weight 1 by n degree of node J, we are basically giving equal weight to all the incoming nodes at J. So, and those weights total sum is equal to 1. So what we see that with this reinforcement scheme, if the reinforcement scheme is of non-Polya type, by non-Polya type I mean that the diagonal A plus B is at least some non-zero number, is greater than 0 and less than 2, it's not diagonal. Or if this condition satisfies, that the set of stubborn vertices is non-empty, such that for any flexible vertex, there is a stubborn vertex such that stubborn has a path from there's a path from the stubborn vertex to the flexible vertex. So every flexible vertex has some stubborn vertex, so that from stubborn you can lead to that flexible vertex. In that case, if this is just a matrix notation that I'm using here, in that case, the proportion of white balls, or the opinion of the flexible individuals, that converges to something deterministic. You can forget about this complete big expression here. What this says is that the proportion of white balls, or the opinion of flexible individuals at time t, converges to something deterministic. So under this condition 1 or this condition 2, if any of this condition hold, then the limit is deterministic. So you can determine your limit based on if you know how individuals are influencing their neighbors, and if there are some stubborn neighbors in the network, such that they have this network in the network connectivity is such that each stubborn individual can influence one or the other flexible individual, then there will be, in the limit, there will be one opinion that you can figure out about each individual. Is that, I mean, at least the idea here is, I hope I didn't make it too complex.
So I just wanted to follow up. So if A plus B is equal to 2, that is what you call Polya type, and
Yes.
non-Polya type is whenever A plus B is not equal to 2.
Yes, and we also want this to be strictly bigger than 0.
Okay, but if A plus B is smaller than 2, you'd have a non-Polya type, and if A plus B is bigger than 2, you would also call that non-Polya type.
No, this won't be bigger than 2, because when we take out M outside, the row total, we want this row total to be 1. This A and B are numbers between 0 and 1. So then your maximum A plus B can be between 0 and 2. So when I said R is of this form, here alpha is something like 0, 1, 2 up to m. You can give your neighbor 0 balls, 1, 2, 3, or maximum m balls of white color. So here I'm taking out m. And because m, the constant m is not important, this proportion is what plays A and B. So by Polya, you can think of Polya as a diagonal replacement matrix where you only reinforce. Let's say if you see that your neighbor is biased towards something, then you take that bias only. You don't take the other, the opposite opinion. So if your neighbor is biased towards a subject A with probability, let's say with opinion 3/4 and with opinion 1/4 for A complement, then you only consider 3/4 of opinion for subject A. You don't give any weight to the opposite opinion.
I see. Okay.
All right. So this is also if I can relate it to the previous result that I showed in the introduction for our model. When you have a diagonal replacement matrix, then the limit is random, but for a non-diagonal matrix, your limit becomes deterministic. So this is something similar, but on a net. Now we are on a network and we are handling more than one urn, where they can be. So there is an adjacency matrix that plays a role. By this, I mean the adjacency matrix restricted only to flexible individuals. And by Z0S here, so this limiting opinion of flexible individuals, this is determined by this opinion of the stubborn individuals and how the stubborn individuals influence flexible individuals. So this is a this is a matrix block of this matrix where one end is in the stubborn set and one end is in the flexible set. So, and A plus B minus 1 also plays a role here. So the whole limit here is that can be determined through all your parameters A and B, the matrix structure. So the graph structure also plays a role. Your initial opinion also plays a role here. Initial opinion plays a role only from stubborn individuals. Initial opinion of flexible individuals doesn't have any role in the limiting opinion of flexibles. So what this says is that under condition 1 or 2, if you have this kind of a dynamic, then whatever is the opinion of flexible individuals in the beginning, they don't remember that in the limit. So the opinion of flexible individuals and the graph structure determines the opinion of the flexible as well. All right. Now, so if I look now, if I condition on these, so now I want to basically see that when is there a synchronization? When under what conditions all the individuals on the network have the same opinion? Now here I'm only looking at flexible individuals because stubborns do not change, so their opinion will never change, or the proportion of white balls in those urn will never change. So I can only look at the flexible individuals. Now, if I condition that this matrix part, so you can think of this as a weighted average of a stubborn's opinion as a constant, and the overall flexible node's opinion as a constant, the weighted sum of that. So if there is a constant weighted average on the stubborns and the constant weighted average on the flexible, then each flexible individual also synchronize. All the flexible individuals synchronize in the limit. They'll all have the same opinion. Now that opinion is now determined through, again, model parameter A, B, and this constant C1 and C2 that we just restricted on. So you can think of this as if all the stubborn individuals have initial opinion Z0 is such that the weighted average comes out to a constant C1, and the weighted average on the flexible set comes out at some constant C2, then that is what determines your limiting opinion. And if the reinforcement is of non-Polya type and there is no stubborn individual, then the limiting, this is even simpler because there is no stubborn to determine the limit. This is the only effect that flexible individuals have. So each individual has this limiting opinion, which is always between 0 and 1. So under these two conditions, you know that that there is a synchronization. Now, similar to the center limit theorem that we observed for the complete network, we now look at the eigenvalues of this matrix, which I don't want to go. Okay. Anyway, so this matrix played a role here, this Q matrix. And we saw earlier that this rho was an eigenvalue of my adjacency matrix, a reinforcement matrix, sorry. Now this reinforcement parameters are coming in here, but this also involves the adjacency matrix. So rho is something that captures the effect of graph structure and also the reinforcement scheme. This is an eigenvalue coming from this matrix Q, which has a minimal real part. Now, assuming that these flexible individuals are converging, opinion of the flexible individuals are converging somewhere, and this rho is bigger than half, then there is a center limit theorem that ZFT minus Z star, if you center it by Z star, limiting opinion, and then multiply it by square root T, then it converges to normal. And this matrix is also determined through, so this expression where this theta is determined by, again, model some of the reinforcement parameters AB, and Z star I is the limiting opinion of individual I when I is a flexible vertex, and Z0I is a limiting is a opinion of the stubborn individual, and theta is a diagonal matrix with these as a diagonal entries. And here also the matrix Q appears and so on. So okay, so the conclusion, let me summarize this slide. So whenever you have a graph structure A and the reinforcement scheme, which is of this form that has A and B, and so we saw just in the previous term that under certain conditions, we know that there is a limit. And under condition 1 or 2, we can find that there is a CLT as well. And now you can use this CLT for hypothesis testing or other things, where we also know the variance structure. So this was when rho was bigger than half, and for rho equal to half, again, we have a CLT, but not with square root T, with T by log T. All right, maybe not. So now when the reinforcement, so far I talked mostly about non-Polya type schemes, and when it is Polya type, I had another restrictions. So for Polya type reinforcement, we will only look at connected graphs, which are deregular, such that the scale adjacency matrix is diagonalizable. So for Polya type reinforcement, to analyze the limiting opinion, we do add several assumptions. One is the deregular, and we also assume that the scale adjacency matrix is diagonalizable. So there is a matrix P which is invertible such that you can write P delta P inverse. And we also assume that the initial number of balls in the urn is the same. This we believe this assumption is not necessary, but for the timing we keep this. And if you define the Z bar T for the Polya type reinforcement, if you define Z bar T as the overall average, so you collect balls from all the urns and define this as an average. So not an average, sorry, the proportion of white balls. This is also an average of all the individual opinions or the individual urn proportions. Then under assumption A1 or A2, what we see that the even with the Polya type reinforcement, there is a convergence. Then the proportion of white balls in the ith is the limit of this proportion of limit of the proportion of white balls in the ith or the opinion of ith individual is same as the overall opinion in the limit. And this is for all I, because now there are no stubborn vertices. This is for all the individuals in the network. And in fact, in the Polya type scheme, reinforcement, the limit is random. The ZT, the overall average that we saw, this converges to Z infinity. And this is also something similar to what we saw in the introduction part, that in the Polya type urn, the limit is a random number. However, for a non-Polya type, it is a deterministic. So here also we observe something similar, that in the Polya type urn, in proportion of white balls, or the opinion of each individual converges, but that converges to something random. And we don't know what the distribution is, unlike the single urn here. So this is a simulation for Polya type 1 and how different it can perform for, and why do we need this assumptions. So the first simulation is when you have a network. Let's say in this network, 2 is a stubborn individual, because there is no outgoing edge, there's no incoming edge, 2, 2. So 2 can only influence its neighbors 1 and 4, but it never gets influenced by any other individual in this case. And if I take an initial configuration, which is which can be as low as 0.2 or as high as 0.8 in these nodes, the overall proportion of white balls in all these 6 individuals, they do converge, but they do not converge to the same number. So that's why we need our assumption of deregularity, that each individual should have equal number of incoming edges. And in this case, if you observe that 2 has a constant proportion because it's a stubborn vertex. So the proportion ZT2 does not change over time t. It always remains a constant. And the proportion of vertex 6, ZT6, this started from 0.8, from very high here, but it still converges to something. They are more or less, they're all same in the limit, but that's not what we have been able to show. So if we look at, let's say, take an example of network with 10 nodes, where we have a 2 regular graph. So each individual has 2 incoming edges. In that case, again, we take a very initial distribution, which is very different from each other. So we start on node 1 has a proportion of white balls just as 0.13, and node 10 has 8.857. So this individual is very, very biased towards subject A, and this is biased towards A complement. Even in this case, because this satisfies our assumption, we also observe this in the simulation, that overall opinion, the opinion of all the individuals, they do converge to the same limit. So wherever you start from, they all converge to the same limit, because what's happening here is that although the limit is random, and in each iteration, you see this limit as a random limit. So this is just output of one simulation. In other simulation, they all could go to some other limit. All right, so that's all I have, and I'll just give a summary and conclusion. When we model our opinion dynamics by placing an urn and this ball selection and replacement mechanism, then our important message here is that the initial opinions are important, but they are important mainly through the stubborn agents. And knowing the opinion of the stubborn agents and the reinforcement scheme, you know what the limiting opinion is. So that could be one of the marketing strategy as well, that this can be used for marketing strategies, that if you can alter the stubborn agents, then you can also alter the limiting opinion in the network. And how does the network structure plays a role? through center limit theorem and others, we observe that the network structure plays a role in terms of the rate of convergence, how fast the opinions synchronize on a network, or how fast you see a convergence to a constant opinion on the network. All right, that's all I wanted to talk about today. If there are any questions, I'll be happy to take them. And I'm sorry if I made it too detailed or technical.
Gursharn, that was excellent. We always aim to have a mix of talks of different levels of technicality. So I think this was a good addition to the mix. The floor is open to questions if you have some. As you already knew, Gursharn, I was following. I had some questions along the way. So I think I want to start off with like a very broad question that also outs me as a very applied mathematician. So usually when I think about building a model for opinion dynamics, I would not go to modeling that as urns. Usually I would just say, okay, there's an opinion that lives on like some interval from 0 to 1, and I'll just model that and not worry about implementing any kind of more sophisticated scheme as the one that you've proposed here or talked about here. So I was wondering if you could talk a bit about, as somebody who wants to apply this to something, when do you see use cases that are specific where you say that that's where the urn model would capture what goes on in the real world better than just some vanilla type opinion model?
So normally the opinions are modeled. So through urn models, what you can do is you can take very specific cases also. So like there are several parameters that you have in hand that you can control and figure out what fits best to your real world scenario. So in the let me give an example of voter model where you have discrete opinions, either 0 or 1 about an object. So in this case, you can with the urn models, there are opinions between 0 and 1 first. So there is a constant change, and you do not. It is important in the cases where you don't change your opinion just based on your neighbors. In just one step you are biased towards something, the other you are biased towards the other. So if your opinion today was less than half, it will not be bigger than half the next day. It'll change slowly based on your neighbors. So if you're, let's say, let me give that in with an example of white and black balls. If all your neighbors are dominated with white balls, but you are dominated with black balls, it'll take time for you to get with this urn scheme. It'll take time for you to get dominated in white color as well. So this urn model scheme for reinforcement or the opinion dynamic purpose is important when there is a slow change, or but this you can also, it doesn't have to be a slow change also. There are model parameters A and B that you can control and make it as slow as possible, as fast as possible.
So is it one more thing, since you mentioned that the comparison between if I have more white balls than black balls and so on. So is there, with tuning those parameters A and B, am I able to construct a case where, for example, people adopt very easily to the white opinion, yes, but very hardly to the black opinion? So you have an asymmetry in how, okay. Could you also have that with more than 2 colors?
More than 2 colors is quite difficult.
Okay.
We are thinking to work with a more than 2 colors as well. Because for in that case, it's no longer it becomes a bit complicated, I'll say, and we are trying to work on that.
Well, it sounds very interesting, and to be honest, I think like even from what you've shown here, it's quite remarkable how many very solid results you can get for this model. So I would have one more question, but I do like would offer it to other people as well if they want to ask one. We do have a question in a chat from Alessio, who says, do you observe any critical mass effect on stubborn agents?
What do you mean by not sure what mass effect mean here? So stubborn agents in our case are those who are not getting influenced by any of the nodes in the network.
No, I
So-
mean something different. I mean, usually in opinion dynamics model, what happens is one of the questions that usually posed is how many stubborn agents do you need for your system to reach consensus, to reach to such that the whole system has all the same opinion. If you need just one or you need more than one, so you need a critical mass. That was the aim of my question.
Okay, sorry. So for our model, we do not, we haven't looked at the number of the mass effect, but I believe based on this result, you don't really need the number as long as you can control the, sorry. Yeah, here. So as long as you can control, even if there is just one stubborn vertex, and you can control the opinion of that stubborn vertex. Let's say there is just one stubborn vertex which can reach every flexible individual in the network. Then there will be a consensus based on the opinion of the stubborn vertex.
So the answer is something like it depends on also on the topology.
Yes.
Thank you.
Do you need all of the stubborn agents to have the same opinion in terms of white balls and black balls, or could they have different ones?
No, there doesn't have to be stubborn nodes. Let's say when there is this reinforcement is of non-Polya type, it doesn't require this existence of stubborn nodes in the network.
But if you do have stubborn nodes, and your stubborn nodes have different initial opinions, what's the final state then?
So when there is, let's say, this is a simple example that when this is of non-Polya type and sorry, you said there are stubborn nodes? Yes.
There are stubborn, yeah.
There are stubborn nodes. So then if you can make this average, so this, if I recall, this is just a weighted, scaled adjacency where you just scale your adjacency matrix so that the column sums are 1. And this is just a S cross F block of that matrix where one node is a stubborn and the other is a flexible node. If you can make this, choose your initial opinion of the stubborn such that this vector becomes a constant.
I see. Okay. So you don't have, so you're not flexible in the sense that you can set any initial opinion for the stubborn agents. They have to have like something that fulfills this condition for the result. I get it. Thanks.
So this is something like on an average, each stubborn, the effect of each stubborn on an flexible on an average that comes out as a constant C1.
Yeah, that makes sense. Yeah.
If let's say if one individual is getting influenced by some set of stubborns in a different way than the other flexible, then there's no way you can get a synchronization, no consensus. So they both, each flexible has to be influenced by the stubborns in a similar way. And this condition is also there that so what this is saying is that if each flexible vertex is getting influenced by stubborn in a constant way C1, and from flexible vertices also it is getting influenced by C2. So if as a node, I have two kind of neighbors. One is stubborn and one is flexible. So my overall effect from both these sets should remain constant. In that case, there will be a consensus.
Yeah, that makes sense.
Yeah.
Yeah, great. So if there are no further questions, I'm going to close the session for today. Before I do that, one more round of applause to Gursharn for this very technical but still exciting talk. And thanks to Vasil for nominating her. And then I guess I'll see some of you next week for a seminar then. Until then, enjoy the rest of your week. Thank you for coming. Bye.
Thank you, Alice. Thank you, everyone.